Matt is. And we're live. Hi, everybody. Welcome to Undersampled Radio, episode 30. We have an awesome show for you today, and it's for several reasons. One of the reasons, the most important reason, is that Matt Hall is hosting today. He is running our technology behind the scenes, and it's so far so good, wouldn't you say, Matt?
It seems to be going perfectly, but let's not dwell on that.
Okay.
Just in case we draw unnecessary amount of attention to the technology, and
I will mention,
provoke it.
I will mention this, though. We're an expert, as you guys know, as you listeners know, we're an expert podcasting professional group with never have any issues. Matt's a secondary computer, which is how we host the Undersampled Radio account on a backup computer, is not in the room. Not in the room, folks. So it's pretty hilarious to watch him run back and forth from room to room hosting this thing. Second reason this episode is awesome, I have to shout this out because our audience is the best ever. So here we have, where am I? A microphone. You can't see this if you're listening to the podcast, but if you're watching on YouTube, you can certainly see it. This is the weirdest looking and coolest microphone ever. It has a built-in pop filter. So John Lehman, if you're listening, you can tell me how my audio sounds. But it was donated by another one of our listeners. So that's actually the second microphone that's been donated. And it's awesome. I'm honored to have such a kind and generous audience. So thank you to that listener. And to
a kind and generous audience that hates how we sound.
That's right. Matt has some big news for you guys, and several of you who are listening to this are going to be participating in this first news bullet point. Let it go.
EAGE, so the European Association of Geoscientists and Engineers, annual meeting is in June. We are hosting a hackathon right before it, the weekend before. And imagine my dismay when I got invited to the EAGE workshop on machine learning on the Sunday of the hackathon. Especially after, but both essentially inviting EAGE to sort of take part in sort of promoting the hackathon and proposing a machine learning workshop, then being invited to one on the day of the event that I was organizing. So happily, the conveners of the workshop were absolutely awesome about it, and immediately sort of asked EAGE if they could move the workshop, which they have. So the machine learning workshop will now be on Monday, the 12th of June. It's being, I think it's being convened. Two of the conveners are from Total, and two of the conveners are from IFP in Paris, the Institut Français de Pétrole or something like that. And I also well, I won't say too much, but I'm hoping that we get some teams from Total, because some folks there are pretty interested in the event. So it's like I think I've said that my plan is to try and get more than 50 hackers there this time. So that would be epic, because we haven't had more than I think 22 or something might be the record. So more than double sort of previous record. So anyway, all things pointing and heading in the right direction. So I'm very happy about that.
Excellent. Do we have, is there somewhere we can go to visit the EAGE machine learning thing that maybe has some summary of topics, et cetera?
There totally is. And I should have put that in the what's name, but yeah, I expect you could Google around and find it, but I will put a link to all the workshops.
Completely professional. Completely professional podcasting crew we have here. Being
reminded, I will do that. I won't try and do it on this computer because things will go wrong.
Hey, did I tell you about Numeri? Did you hear about this?
I feel like maybe we mentioned it once because it came up on Software Underground, right? But yeah, what is Numeri?
It is as they say, a new kind of hedge fund where they accept buy-sell predictions from their, hey, look at this. Lucas is posting the link that right there in Swung. Sorry, Numerai is a hedge fund that takes predictions from its sort of crowdsourced opinions about buy-sell recommendations. So you build a model and you submit your predictions, and if you do a good job at predicting, they pay you money for your predictions.
Right. They pay you
cool.
Bitcoin, right?
Yeah.
And the deal is that they release new data every week or something, and you make predictions for the following week, or how does what's the sort of cycle?
Yeah, that's right. So it's a new
data.
It's a new data set every week, every 7 days. The data is anonymized and encrypted, so you don't actually know what stock information you're looking at. All you receive basically is encrypted feature vectors, or just random floating point numbers, and you build whatever kind of model you want, and you submit your predictions on. They give you a training every week, a training data set, and a prediction data set, which is a tenth the size of the training data. And it's kind of cool. So you can do whatever you want. I built a deep neural network feed forward to do this, because you don't really know that much about the structure of the data. I'd be interested to hear from our guest in a little bit how you might apply some recursive techniques to it. So anyway, check it out, numer.ai. It's pretty cool.
It sounds really interesting. It makes you, just reminds me I mean, it's not the same at all, but there's a thing in Norway that I'll try and remember to put a link to, where you can, I think it's actually an app, a mobile app, and they basically get people to vote on the outcome of wildcat exploration wells. So they're trying to sort of crowdsource, basically see if the crowd can match or beat any other kind of prediction about what the success rates are going to be, and maybe inform risking of future wells and that kind of thing. But I love that idea of kind of crowdsourcing opinion like that. I wonder what a Numerai-like model could do with the oil price.
Well, there is certainly more wit in the crowd than there is in an individual.
Yeah.
Which is why I'd like to source some opinions from our crowd of one today. We have, how bad was that? We have Dr. Jackie Floyd here on the line with us. She is a research scientist and I think owner of Element Labs List.
Yeah, or principal. Yeah. It's a company registered in Texas. So
cool. Well,
LLC.
Welcome to the show.
Thanks
for coming on. We'd like to hear a little bit more about, and I said it backwards, it's Element List Labs. What you actually can find a link to that in the show notes, Matt. So tell us a little bit more about Element List and what it is and what it does.
Well, Element List Labs is like kind of like a meta company or something. I started it back in May when the startup I was working at kind of ran out of money, and I'm using it kind of as a home for basically a lot of all my research, all my little side projects, everything that I've been either working on in the past, for example, Element List, to new projects like some work on natural language processing that I've been doing lately, and it's all kind of under the Element List Labs umbrella. And so lab is really just a great way of saying, this is my little playground and anything can happen here. And the Element List name really just came from this old website that called Element List that I actually started in 2004 and ran it for a few years, and then moved on to other things in the internet world, and then took the site offline and literally just like fired up the old code. Got some upgrades in the last few months, and the inspiration for elementlist.com, well, in 2004 was the fact that research groups, and at the time I was at Lamont Doherty's Observatory at Columbia, were being asked by National Science Foundation to put all of their databases online, and that was still pretty early days, right? I mean, Google had only been around 5 years at the time, and so I said to myself, well, there ought to be a place you can go on the internet to find all of these databases. and, other information. So I just, kind of puttered around on the internet and put this website together, and then suggested I add a blog to it. So I added a blog, and I started blogging about science. And every time I would, I was adding things to elementlist.com on my own. And when I'd come up with something interesting, I'd blog about it. And I ended up getting emails and notes from CEOs of little startups, and eventually was starting getting invited to conferences, because there really weren't that many science bloggers at the time. And I went to the first ever science blogging conference. I was invited to Google SciPoo conference, which is an invitation only thing run by Tim O'Reilly and some people from Nature. And so I went to that, and I got to meet Larry Page, Sergey Brin, Martha Stewart was there. She was actually the +1 for Microsoft exec, who was her boyfriend. It was an interesting conference. And I think she'd been out of jail for about a year, and she was joking about that, which is funny. And anyway, I decided like the whole internet world is much more interesting than what I was doing at the time. I was at Exxon when I was starting to get invited to these conferences. And so I left Exxon, went back to New York. I've been wanting to get back to New York, and kind of jumped into the internet world, doing, at the time it was called analytics, web analytics, but now it's kind of morphed into data science and machine learning. And that was sort of like my introduction to sort of the big data world. And then the last couple of years, I've come back into geophysics, managed to move to Texas about 6 months before the oil prices plummeted. And yeah, they got picked up by a startup called S-File about 1.5 years ago that's focusing on machine learning and natural language processing for oil companies. And so finally, like just in the last couple of years, I've been able to kind of merge data science / machine learning with geophysics and kind of bring those two fields together.
Which is basically the entire thrust of this podcast. Every single episode, we talk about machine learning as it applies and not as it applies to geosciences. So I'm just going to jump right to the big one that I want to know here, because I want to do this. What are people paying for? What are companies paying for in the geo space, in the geo machine learning space?
Well, yeah, that's a good question, because I don't know how much I can say about my former startup. I'm probably bound by whatever piece of paper I signed. But right now it's a matter of getting all of the data, because oil companies have tons of well logs that are just, for example, they're just GIFs, and just images and literally like hundreds of thousands, and they have data, stored in like Excel files, and they get reports sent to them by email rather than like in a nice data stream going into a nice database. And then you have like, still have plenty of paper copies, like in, caves or basements, and so right now I think part of the challenge is just kind of gathering up all that data, because I was just reading an article about this the other day. The real value is in the data. I mean, nowadays, you can download TensorFlow, you can, read about all sorts of, different algorithms that are out there. I'm sure there's a learning curve, but without the data to train it on, they're not very useful, right? And oil companies have always been very protective of their data. So it's actually, I think what I found is it's going to be hard for the consultants to really penetrate, because unless you have some secret sauce or something that they can't come up with, on their own, or just hire more data scientists, that you have to have access to that data, right? To start to build a model or do something predictive. And there are still startups on the outside that are working their way in, which in some ways is necessary, because oil companies are so conservative by nature, and they're kind of slow to jump into this area, which I experienced being at an oil company trying to do machine learning here in Texas just within the last couple of years. And but I think that, let's see, what was your question again? I got off track.
I guess the summary of the question is, what kind of commercial applications are there for machine learning in the geo world?
Well, obviously you want to be able to predict where the oil is, right? Where to drill, and then in the more complicated cases of say fracking, you want to know how to complete the well so you can maximize your production. So there might be all kinds of combinations of parameters, what kind of, I don't know, SEO do you use or something like that that can influence the productivity, which is also, it's not just the engineering part, but also whatever particular geological type of rock you happen to be in. Are you in a shale, or are you in a limestone, and sandstone, et cetera? And then maybe what kinds of oils you have. So that's a machine learning problem, being able to come up with the right combination of parameters for a given well in a given formation to know what you need to do to maximize production. And you could do that in a sort of static way, or you could do it in a dynamic real-time way. And obviously, the closer you get to real-time, the better, because then you can respond to things. But even in the, I guess I call it more, static approach, or just looking at historical data, you can at least start to make business cases for why you should drill one well a particular way, or, to your management team.
Mm-hmm. So 5 years from now, down the road, do we need geological interpreters?
I think those, we're going to need them. We're going to need them. And in fact, the interesting thing that I saw, having been sort of a geophysicist with machine learning skills in an oil company, and then a geophysicist in a tech company surrounded by computer scientists, is that there's a gap. There's a gap in skills, and there's a gap in kind of just the language and terminology and mindset that people have. So just to give an example, there was a case where I was working with some computer scientists and on gathering data, and there's some geochemical data, and that they thought it was messy, right? Because it's not. They thought that the seismic data and the digital well log data was so much better because it was nice, clean, precise numbers that they could calculate, but they didn't really know how to deal with like these oil measurements that were made by a mere human in a lab, right? But the oil, that's the stuff you're trying to get out of the ground. That's the gold, right? And so the fact that they didn't see that, or that it took a while for them to catch on, was just sort of an example to me of the kind of biases that computer scientists have, and how someone with a good geological and geophysical background can identify opportunities that someone with a pure CS background would miss.
Mm-hmm. Yeah.
Long answer.
Well, yeah. I mean, I think it's really interesting, right? Because it's always been, I don't know if I'd call it a barrier, but certainly a fear for the adoption of AI. I guess probably in any industry, is that it's going to take jobs away. But we've talked before on the show about how we feel like it might actually make jobs more interesting. But because it focuses you on the things that actually are really unknown, and not the things that you just sort of need something to go interpret, right? No matter how mundane or whatever. Now, maybe it takes fewer people to do that really interesting work. I'm not sure. That's a problem that might have taken care of itself in the last sort of 2 years. But I wonder if there's a sort of literacy gap then that somehow needs to be filled. And what do you think are the, a lot of people are obviously newly out of work, or they're doing a geophysics degree right now and wondering like how they can be useful in the job market. Like, what do you think are some of the sort of gaps that need to be addressed if we are going to be working on those interesting problems, and they're not just going to disappear off into the realm of computer science, never to sort of involve us again?
Yeah, so I think the domain experts are in a better spot than the computer scientists. I mean, the computer scientists are still, classifying numbers and cat pictures and because they don't have the domain knowledge of geology or geophysics, they don't know what problems to tackle. But if you were to give a geologist or geophysicist the computer skills, and you don't, obviously more is better, but if they knew, some basic algorithms, some object-oriented programming, they move away from Fortran and MATLAB, which I'm sure is great, but really, they need to be learning how to, code better. then it won't run away from them. They'll, in fact, I think the geophysicists and geologists are in a better spot to come up with new and interesting applications. And the jargon around machine learning is sort of intimidating at first, but I've found that that actually, especially geophysicists, already have most of the math and quantitative background. We do signal processing. We know linear algebra usually. The calculus, physics, all the kind of quantitative stuff. But there is some jargon and a way of thinking when it comes to computer science, not just coding, but the computer science behind coding that could make geologists and geophysicists better at coming up with their own models. And I think what someone earlier asked about deterministic problems, I think there's going to be a good mix of using statistical approaches to some of our more classic geological and geophysical problems that could produce interesting new results.
Right.
To be really vague.
Yeah, no, I mean, I think it's a huge opportunity, right? I mean, I really hope we see more people getting that literacy, learning some of the jargon so they can communicate and read papers, and not being too intimidated by that initial, the shock of the new kind of thing that can, I think some people just get kind of turned off by it. But I think this year is going to be a really right at the time we're in right now, it's going to be really interesting to see people making that, jumping that divide kind of thing. I've been really blown away lately, but I've been going through a lot of bibliographic data, and I'm really noticing just how far back the machine learning literature goes. In geophysics, there's tons of articles from the 80s about neural networks for predicting lithologies and well logs and production. And, even recurrent neural networks, there's a paper on that from 1990. That's 27 years ago that people were working on that stuff. It's kind of amazing, right? So it's been making me wonder, what's different now? Has anything changed? Why didn't it take off back then if machine learning's so awesome?
Well, I think it was really pushed by companies like Google, right? Because they were the first type of company, and I could just say all online companies, including Amazon, Facebook, but they really had to deal with just all these streams of data from users clicking, right? And they didn't have the sort of hang up that a lot of, I'll just say, earth scientists have, of assuming that you have to know every little point in a process. You have to understand the details before you can understand the macroscopic picture, right? But Google is we don't necessarily need to know just yet exactly who our user is that's clicking on this ad. We just need to know, for instance, that they clicked or they didn't click, and we count one as a win and one as a loss, and then we optimize for those clicks. And then as things sort of progress, they could get more information on people, where you are, what time of day, what kind of computer you use. And then when they, you have companies like Facebook, now they can use biographical information about all your relationships, and Google's doing that too. So it's kind of grown, but they had the challenge early on of building the infrastructure, including, big data centers and then algorithms that allowed them to get ahead. And so the oil companies will catch up, for example, but I think it's really been driven by just the internet technology companies. And of course they have all the big AI teams, right? So I think that's been the hang up, and the fact that they're doing so well and they're jumping into, self-driving cars, and it's getting oil companies' attention, and they're starting to hire now.
Yeah, right. But do you think all of that, so the fact that the landscape outside of kind of, this, I guess, the pure research that was being done 25 years ago, do you think that's going to make a difference for how far we get, so to speak, with AI kind of this time around in oil and gas, or in subsurface, or science in general?
Yeah, I think so. I mean, well, one of the big problems, just, I'm a little biased because I come mainly from like the reflection seismology world, and world of like 3D seismic processing, acquisition, and everything. And it's always been the most expensive project, right? And some of the first people to get cut when oil prices go down are the geophysicists, and they slash budgets for collecting new data sets and doing fancy processing programs, because the value to an engineer isn't always obvious, especially when like the best resolution that you can get is maybe 30 feet or 50 feet down deep, and they're like, well, for less than the price of collecting a 3D survey, we could just stick a well down in Oklahoma and test it and collect our well logs, right? So I had those conversations all the time with engineers about the resolution issue, and it was something that we never could overcome, right? And so, but also the other issue is the cost. Now, if we could bring the cost down, if we can't, because right now seismic data processing is still too manual. People having to edit data and pick velocities, and like the whole process is very slow. If we could reduce the processing time on 3D seismic data, then that would help geophysics as an industry, or help what we do be valuable sooner to oil companies, because the delay, that's another factor. It takes, it could take months to get the seismic project approved, months to collect the data, months to do a first pass processing, then you do all your migration. It could be like well over a year between the time you approve a project and start to see some results. So if we can shrink those down with machine learning, that would be a big advance.
Yeah, I have this sort of, I should probably try and find some data to actually corroborate whether this is what really happens. But I have this sort of pet theory, I guess, that actually these projects, if you can basically do it faster and cheaper, then, and I don't know if this is just sort of CGG going, oh, here's an opportunity. Well, now the opportunity is to, add some new dimension to the data, or some new level of complexity, or some supposedly better level of imaging, so that it takes the same amount of money and it takes the same length of time. We're actually just pushing those sort of incremental, what you hope are quality improvements, but what I think are actually, I think we actually have gone beyond now what the level of certainty that we can cope with in the interpretation process. So do you know what I mean? The expectations get inflated, right? So sure, you can do it cheaper, but I don't want just a 3D preset migration by itself is not enough anymore. You want all the attributes, right? Exactly. And then you want to do all the fancy modeling with the attributes and the well data. So, but that's great. At the same time, it means you can do that, right? And if more people can do, that for overall less cost, or more for the same amount, then it's still a win. Yeah, it's still a win, totally. If I guess if you think we actually can make use of all of that extra information, right? Because I wonder a little bit if actually we haven't really figured out just how to do good, reproducible structural interpretation in a very simple way in 3D, let alone stratigraphic problems and subsalt problems, and like those are. Maybe I'm exaggerating the difficulty of the problem, but it does occur to me that these sort of projects expand to fill the space or the budget available. Oh, you can do it cheaper. Now we'll do more.
Yeah, and that's well, it also comes from maybe overthinking the problem, or I guess it depends on at what level you're talking about. If you're really trying to get some very precise results in a specific location, or if you're happy with just getting a whole lot of data to find, a whole bunch of, potential hotspots where you could drill, right? So in the big picture case, the images, it might be blurry at a certain point, but you can do the next round of processing or evaluation when you get to some smaller scale, so depends on the problem.
Right. We were talking the other week about how maybe if AI turns out to be as awesome as we think it can be, maybe you won't even need to do imaging anymore, and the AI will just take your shot records and produce interpretations, or not even bother interpreting. Like, maybe you don't need interpretation. Maybe that's a human crutch, the sort of geological step. Maybe it can go straight to oil finding, which, as you say, is the sort of goal.
Yeah. I guess that, well, you saying that made me think or recall just the fact that there is already so much data. I mean, there's a ton of, especially on the onshore areas. Right. There's well logs going back to the 30s or 40s, and if you want to now, you could potentially scan them off of, the page. Well, now most of them are scanned as far as I know. And then now you want to get the values off of those logs. You want to get the digital values, and then you want to pump those through your machine learning algorithm. I think it's possible we might, if companies can mine their old data better, they might not need new data all the time. They might have enough, right? And it's just not being mined effectively right now. So I want to bring up examples, but I might be giving away company secrets. But I mean, I was at one, I'll just say an oil company. I've been to a few, so I don't have to reveal which one. And they had bought almost 1 million well logs for like $1 a piece. And I said, that's a big data problem. We should, use that. We should use machine learning to study all these logs. And instead, the geologist jumped down my throat immediately. And it was actually very hostile. Their reaction was very hostile. And from no, you could never do that, it won't work, computer can never interpret like a human does, to what if she's right? That's my job that's going to go away. Because right now, all that not all, but some of the basic tasks of geologists to pick well logs, right? And then geophysicists are, considered the people who draw lines on seismic data. And those are two very manual processes that really could be done probably better by a computer and over bigger, large data sets. And if the geologists don't want the computer scientists to kind of come in and take their jobs, well, that's where the geologists and geophysicists can take advantage of their domain expertise and maybe write their own code, right? And so that they know what the code is doing, and they're confident about the results that they're getting. And that's going to take a bit of it might be a generational change, because you're going to need more people with the coding skills to, tackle some of those problems. Like that, I noticed the challenge that you have for this month, I guess, is to in the leading edge, right? Is to predict lithologies from well logs. That's a great project, and I think that that'll get people's attention, and maybe get there'll be more people if they have the freedom in their oil companies to start doing some of that in-house.
Yeah. What we haven't, I don't think, seen yet, because I would encourage people, like in the situation of the person who freaked out when you suggested using AI to look at those well logs, is like, even if you aren't part of the coding process, at least be part of the sort of code like the formulation of the problem and informing the the way that you attack it with feature engineering. And I mean, essentially all that's basically just doing petrophysics. It's encoding stuff. It's just that now you get a really good idea about whether it worked or not, instead of a kind of, oh yeah, that looks geological kind of yardstick, which is kind of, I feel like, what we generally use these days. It's like, yeah, that looks right, or that came from that book, so that's legit. There's very little like, well, can I actually validate this against my data set? Which is, I think, one of the kind of key things in quote unquote data science that people need to pay attention to, like rigorous cross-validation and the total kind of, well, being as objective as humans can be, right? Because we're not always objective. That's one of the kind of cornerstones of good data science. And I think as a geoscience community, we do well to pay more attention to that. It's a good principle to have.
So we've just had a listener post a question, or not a comment, which I'm going to phrase as a question, which is kind of an interesting concept. He mentions that it must be possible to use a machine to find oil for us, because it's a binary classification problem, right? I mean, is it water or is it not water saturated? And I'd like you to touch briefly on whether or not you think that is an achievable goal, and what kind of training, data, and pre-processing steps do we need to cope with before we start asking machines where to drill for oil?
Well, it depends on what your data is, right? I mean, just say, is it water or oil? Is it seismic data? Are you looking at well log data?
Yes.
Yes. Well, if you have it all, then you're lucky, right? I mean, if you have well log, that means you've already drilled in, so you would know what's there. There's not much mystery to that. Then it's kind of a mapping problem. But I think that the machine learning problem in this case is when you have sparse wells and maybe a big 3D data set or multiple 3D data sets that are kind of sewn together. And the trick is that when it comes to trying to figure out what the rocks are, you have a little limited response, right? You could have there's certain things that affect the velocity, certain things that affect the density. If you don't have AVO information, for example, you won't be able to get elastic property information. So it's not such a simple problem. But I think actually what got me in touch with Matt over a year ago was when I was using self-organizing maps to try to classify areas of a reservoir and try to predict along with oil production information. So that was useful, but it in that particular case didn't get off the ground, or the only way to test it is to drill, right? And I did that. I started it before oil prices fell, and by the time I was done, I think it was like December, and oil prices were looking pretty bad. So
it's interesting to hear you say that, because just over the last couple of weeks, I've been building a self-organizing map thingamajig to do AVO analysis and reservoir differentiation. And so far, no dice. So is your project closed books off the record? Was it for an oil company, or is it open?
No. And I couldn't. Well, I left before I could finish it, and then probably couldn't have published it anyway. But or at least that particular data set. But I used principal component analysis first to kind of clean it up, and so in our case we had 64 or so seismic attributes, and with principal component analysis, I guess we reduced it down to maybe 10 or components with information, and then put that into the self-organizing map, and we got much better results than if we tried doing it without principal component analysis.
Was that sort of on a sample by sample basis, or did you break out the wave field into particular events or seismic pieces or anything?
It was from the seismic volume, so it's actually like little raster values for each.
Right. Okay. The reason I ask is the path I'm going down at the moment is to take multiple attributes, as you say, but build a feature vector such that the inputs encompass a wavelength's worth of information. So if you're using shot records, for example, or image records, the input feature vectors the prototype vectors would be sample waveforms built from AVO modeling, and then the vectors you're trying to classify would be extracted wavelets from true seismic data and its derived attributes.
Why are you looking at the waveforms and the offset as opposed to just, for example, intercept and gradient?
Sure. I just wanted to try something in the sort of time-space domain before moving into those more abstract attribute spaces.
Yeah. What I did this is actually a master's project way back at Columbia, was I used the genetic algorithm on the stack trace, mm-hmm. and just try to model velocity and thickness, and mm-hmm. then happened to find areas of low velocity and or density, and then use AVO to try to break out those areas. So in the 1D case, you're just looking at thickness, you're looking at kind of a vertical, semi-vertical structure. And in the AVO case, you're trying to extract the velocity, density, or you might say elastic attributes, depending on what you're looking at. So you might kind of break the problem apart into 2 steps.
Yeah, it's a really interesting approach. I like the idea of sort of building dimensionality into the problem to tackle different pieces of.
Unless are you doing forward modeling?
Well, that's the idea. I'm not there yet, but that is where I'm headed. So I want to ask a completely tangential question. We have a note in the show notes here about the non-commercial aspects of machine learning as it relates to geo stuff, or maybe not even geo stuff. We've been talking sort of about industrial applications, commercial applications. What about research projects? Something very forward-looking, or something that doesn't relate to industry in any way? What's your favorite thing going on right now?
Well, so far the things I'm focusing on, I'm kind of selfish. I'm focusing on things that are useful to me, and I figure if I can make them useful to me, then maybe they'll be useful to other people, and if they're not useful to other people, well, then they're still useful to me, and so I might not make money off of it, but it can help me do my work better or faster. Yep. And one area that I've been working on is natural language processing using word embeddings, which has gotten pretty popular on the internet. Lots of people have been using word vectors, for example, to classify whiskey based on whiskey reviews, and I've been doing it because I'm lazy and I don't want to have to read all of my geology papers. And one thing that I've encountered, especially doing more onshore exploration, is when you go into a new area, whether it's like maybe New Mexico or Texas or Oklahoma, you have to learn all the formation names and all the rock types and everything. And but if you could use a natural language processing algorithm to just sort of extract those words, say what minerals are in the such and such formation in Texas, then that would be really useful. And so I made a kind of, I don't know if I want to call it a prototype, but I have a program that does that, and I presented some initial results at AGU last month. And so basically I ran Word2Vec on about 300 papers or so, or how many, I forget how many it was. a few hundred papers from some areas I had studied in the past. One was the Woodlark Basin in Papua New Guinea, which is a active rift. Another one was Hess Deep, which is another rift in the Pacific, and then some area. The Gulf of Mexico Basin and surrounding areas. So what I was curious about was, what could the model learn about rifts, and could the model help me learn things maybe about one rift based on information that is found from other rifts, right? So maybe there were some commonalities, or some relationships that it could learn. And so I did that, and there were some really interesting results. For example, it learned the geologic timescale just from word usage in papers. So I could, so there's let's see, it goes Triassic, Jurassic, Cretaceous. If I picked the word vectors for Triassic and Cretaceous, I knew that Jurassic was the middle one or nearby, and I could march through the geologic timescale with all the names of the eras and periods, and it had learned those. And if it got one wrong, it usually meant that I didn't have enough papers for covering that era, so I'd grab a few more and throw them in the batch, right, just to kind of map it out. And so that was interesting. And then the next step was to kind of classify types of words, classify mineral names, types of rock names, formation names. What were the others I used? Obviously, geologic ages, and structural names. Whether it's a fault or a hill or like a graben. And so I use a classification algorithm to just classify word vectors for those 5 groups, and then I said, well, wait, I don't need to classify like the 50 states. I already know what those are. So I created a list of 50 states. I don't need to, classify the elements in the periodic table. I know what those are. So I threw those in a list. And then I said, okay, now for a given query, for example, I used Hess Deep. I said, what structural terms are most closely associated with Hess Deep? And what elements, what rock types, what rock names, and it could find those. And it came up with one really interesting result, because I also ran it against states, because that's just how it worked. Running everything against states, even though Hess Deep is out in the Pacific, it kept coming up with Mississippi. And I left that result in when I showed the poster at AGU, and people were like, why is Mississippi there? It doesn't make sense. And then it occurred to me that Mississippi is actually the failed rift arm from when the Gulf of Mexico opened. And so it actually makes sense that, Mississippi would be affiliated with Hess Deep rifts, out in the Pacific. And which, that's something that a computer scientist might miss if they didn't actually know a little bit of geological history, right? And so it's one thing that I think is useful. I might not have the best AI algorithm, compared to, I don't know, whatever they're doing at Stanford or Oxford or something, but I can get it good enough so that I can get some useful results for myself, and then my domain knowledge comes into play, where I can kind of pick and choose among the results, and it's almost like you might say a kind of recommendation algorithm. I'm not expecting it to give me the most accurate or the accurate result, but I'm hoping it'll give me some suggestions or ideas that I could then explore further.
Yeah, wade through all the nonsense for you.
Right, and then you don't have to read all the papers, right?
Yeah.
or then you know what to look for. You might say, okay, well now I'll go back and I can do a search, and I can just find those papers with some keywords. But the one thing that's really cool about it, compared to, for example, just doing a word search on paper, sure, you'll get the whole paper, but then you have 30 pages or more to read. Whereas this is actually kind of reading all these papers for you and finding things that are useful. So.
Yeah.
Pretty cool.
That's fascinating. Actually, we'll put a link to the AGU paper in the notes here so that people can look at it, along with your publications in Nature and in Science, which is about the most impressive thing I've ever seen. Dr. Jackie Floyd, I want to thank you for coming on the show today and giving us hope for the future.
Yeah, thanks,
Thank
Jackie.
you.
It's good to meet you.
This is fun. Yeah, good meeting you.
Guys, we'll see you next week with Chris Jackson on the show. Episode
I need
30.
to unplug us, don't I?
Yeah, thank you. I was trying to cue you in on that. Yeah. Okay, thanks, guys. See you next week.
Okay, bye.